partial differential equation. Today I will discuss the non-linear partial differential equation of order 1 and maybe degree more than 1. Before that, I am going to discuss few definitions related to the solution of the partial differential equation. Now let us start with the definition of complete integral. So let f of x, y, z, p, q equal to 0 be the partial differential equation. It can be your linear partial differential equation or non-linear partial differential equation, and say its solution is and phi x, y, z, a, b equal to 0 is the solution of given PD, given partial differential equation. Now then, complete solution. This solution, the solution phi x, y, z equal to 0, phi x, y, z, a, b, 0 equal to 0 is known as complete solution and have constants a and b. So this is known as complete solution and it has two constants a and b. Then particular solution. Now if you put some particular value to the constants a and b, then this solution is known as particular solution. So solution phi x, y, z, a comma b is equal to 0 is said to be particular solution if we put particular values of a and b. If we put particular value of a and b, then this solution is said to be particular solution. Then singular solution or singular integral. Singular solution or singular integral. Let phi x, y, z equal to 0. This is your solution. This is the solution of PD and this is known as a complete solution. And then also differentiating one partially with respect to a and b, also on differentiating, or you can write it as now eliminating small a and b from 1, and now if we partially differentiate this equation number a with respect to a and with respect to b, then on eliminating small a and b from 1 and with the help of these two equations, the solution which you are getting after eliminating a and b is known as singular solution. So that means you can say that in the singular solution we will not have the constants a and b. So if you eliminate a and b from equation number 1 and these two equations, then now eliminating a and b from 1 and these two equations, our solution is known as singular solution and it is free from constants. It will not contain any constant like a and b. So this is known as your singular solution. Now let us consider general integral. Let f of xy, let phi of xyz p a comma b is the solution of given PD, and say it is your equation number 1. Now if it is solution of the given PD, then let us assume b equal to some function of a. Say b equal to some function of a, and we have assumed that b equal to psi of a. Let us assume this value for v. Then now on eliminating a, now if we put this value here, then we have, now this equation will be phi of xyz a comma b. Now b is psi of a equal to 0. So this is equation number 2. Now if we eliminate small a from this equation, and on eliminating a, now we have just one constant. So on eliminating a from, say, from 2 and del phi upon del a equal to 0, we get general integral. Charpit's method. For partial differential equation of order 1 and degree may be more than 1. So that means we can solve the nonlinear partial differential equation. So let f of xyz pq equal to 0 be the given partial differential equation. If this is your given partial differential equation, then as we know that z is function of x and y, so we can write z as dz as also dz equal to del z upon del x dx plus del z upon del y dy. Now we can write dz as del z upon del x into dx plus del z upon del y dy. Then this will be your, now del z upon del x is p, so this is your p dx plus q dy, or you can say that dz equal to p dx plus q dy, as your p is del z upon del x and q is del z upon del y. Now on integrating this equation, we will get our z, and z is your solution of this partial differential equation. Now main problem is to evaluate the partial derivatives p and q. Now p and q are evaluated with the help of Lagrange, with the help of Charpit's auxiliary equation. P and Q are evaluated with the help of the Charpit's auxiliary equation. And what is Charpit's auxiliary equation? It is given by dx upon fp. Fp stands for the partial derivative of f with respect to p, equal to dy upon fq equal to dz upon p fx plus q fq, then minus dp upon dx upon fp plus equal to dy upon fq equal to dz upon p fx plus q fy, then dp upon fx plus pz, excuse me, this is your pfp plus qfq. Now this will be your fx plus pfz, and here we will get minus dq upon fy plus qfz. Now this is known as the auxiliary equation of Charpit's, which is equal to dx upon f, that means the partial derivative of f with respect to p, equal to dy upon fq equal to dz upon pfp plus qfq. This is your pfp plus qfq equal to minus dp upon fx plus pfj, and this is equal to minus dq upon fy plus qfj. Now some author used to write it as, they used to write this minus sign here. So if you multiply this whole equation by minus sign, then we will get dx upon minus fp equal to dy upon minus fq equal to dz upon minus pfp minus qfq equal to dp upon fx plus pfj and dq upon fy plus qfj. That is another way of writing this equation, but it is easy to learn this formula, so I will deal with this formula. So let us solve few questions related to the Charpit's method. Solve the following using the Charpit's method. Solve using Charpit's method. The first problem is z equal to px plus qy plus p square plus q square. Second problem, zpq equal to p plus q. The third problem, z square p square z square plus q square equal to 1. These all questions are very important for exam purpose, so I am trying to solve them. This is your fourth one. Then fifth one is q equal to z plus px whole square, and the sixth one is p square plus q square of x equal to pz, and then we have the seventh problem as pxy plus pq plus qy equal to yz, and the eighth problem is p square x plus q square y equal to z. So I will try to solve these questions. Now let us solve question number 1. So starting with Charpit's auxiliary equation. So Charpit's auxiliary equation is dx upon fp. Before that, let us write it as solution of the first part. Let us write f as z minus px minus qy minus p square minus q square equal to 0. Let us assume this expression as f. Now if this is your f, then using Charpit's auxiliary equation, your Charpit's auxiliary equation is dx upon fp equal to dy upon fq equal to dz upon pfp plus qfq equal to minus dp upon fx plus pfj and minus dq upon fy plus qfj. So this is your Charpit's auxiliary equation. Now from here we will have dx upon fp. Now the partial differentiation of f with respect to p. Now the differentiation of p will be 1, so we will get minus x. And now as we are differentiating partially, so the differentiation of z will be 0, differentiation of qy will be 0, differentiation of p square will be minus 2p. So this is your f of p. Similarly, your f of q will be minus y minus 2q. Then your dz will be p times this term minus plus q times minus y minus 2q. Then we will have minus dp upon fx. Now the partial differences of this term with respect to x will be your minus p. and rest differentiation will be 0 because we are differentiating partially with respect to x. So we have x and the differentiation of x is 1, so we will get minus p. Then we will have p into fz. Now the partial differentiation of this whole expression with respect to z will be 1. So this is your p, and similarly this is equal to minus dq upon fy. Now the partial differentiation of this term with respect to y will be minus q, and then this is your minus q, and then we will have q into fz. Now again partial differentiation with respect to z will be your 1 because here we have z, so its differentiation will be 1, and differentiation of px, qy, p square, q square with respect to z will be 0. So this is your Charpit's auxiliary equation. Now from here you can see that this is your dp upon 0 and this is your dq upon 0. So on cross multiplication we will get dp equal to 0. This is your dp upon 0. So on multiplication dp upon 0 equal to this term. So that means dp equal to 0. Similarly we will have dq upon 0 equal to this term. So again your dq equal to 0. So on integration we will get p equal to a and q equal to b. So if p equal to a and q equal to b, then now dz equal to p dx plus q dy implies, now as our original question was, now because z equal to px plus qy plus p square q square, therefore your solution is z equal to, as we have the value of p as a, so this is your ax, then we will have dy plus some function a square plus b square. So this is your solution also. So this is your solution. Now if you use this formula dz equal to p dx plus q dy, then let us see what happens. Now then you will have, as p is a, so we will get a dx plus b dy. Now on integration, the integration of z will be, dz will be z. Now this will be your ax, and here we will get dy plus some constant of integration. So we will get c. And here you can see that in place of c, we are getting a square plus b square. So both solutions are equivalent. So this is your solution of the problem number 1. Now let us solve second problem. Or you can solve second. I am solving the third one because second problem is, I think, quite easy. So let us solve third problem. So let f equal to z square, p square, z square plus q square minus 1, or you can say equal to 0, or f equal to p square z4 plus z square q square minus 1 equal to 0. So Charpit's auxiliary equation is dx upon fp plus equal to dy upon fq equal to dz upon pfp plus qfq equal to minus dp upon fx plus pfz equal to minus dq upon fy plus qfz. So this is your Charpit's auxiliary equation. Now if this is your equation, then put the value of fp, fq and fx, fz. So this is your dx upon fp. Now the partial differentiation of this term with respect to p will be 2p z power 4. And here dy upon partial differentiation with respect to q will be 2q z square. Similarly we will have term for, now you can, I am not writing this term because I think there is no need of this term. So this will be your pfp plus qfq. Now it is equal to minus dp upon fx. Now you can see that your fx is 0 because there is no term of x. So your fx is 0. So here we will get p into fz. And similarly, again you can see that there is no term of y. So this will be your minus dq upon q into fz. I am not writing the value of fz because you can see that this fz is cancelled from dp upon p and dq upon q. So from here we will get dp upon p fz equal to minus dq upon q fz So now as you can see that fz is cancelled, so we will have dq upon b equal to dq upon q. So on integration, please, okay. So on integration, we get, now the left hand side will be log p and the right hand side will get log q plus some constant of integration, say log c. Now log a plus log b is log ab, so we will get p equal to some c into q. So this is our p. Now let us find out the value of q. So put the value of p here, because z square p square z square plus q square equal to 1. So put p equal to cq. So if p equal to cq, then this will be equal to 1. So from here our q will be, now let us take q square common. So this will be equal to 1. So from here we will get q equal to 1 upon z under root c square plus z square, c square z square plus 1. So this is your q. Now if it is q, then p will be, therefore p equal to cq equal to c upon z under root c square z square plus 1. Thus we have the value of p and q. Therefore, using now dz equal to p dx plus q dy. So from here we will get dz equal to p. So this is your p, which is your c upon z under root c square z square plus 1 plus q into dy. Now if you take this term common, then we will get z into under root c square z square plus 1 into dz equal to c dx plus dy. Now if we take c square z square plus 1 as t, let c square z square plus 1 is equal to t, then you can see that you will get 2. Now let us differentiate this one with respect to t, then you will get the differences from z square will be 2z. So we will get 2c square z dz equal to dt. So from here we will have z dz equal to, so we will have z dz equal to dt upon 2c square. So therefore, now this will be your z dz is dt. Now this will be your under root t, and in the integration of root t will be 3 to the power 3 by 2 upon 3 by 2. So we will get 1 upon 2c square, as z dz was dt upon 2c square. So we will get 1 upon 2c square. Now here we will have under root t into dt. Now the integration of root t will be, so let us write it as a on integration, on integrating a, we get, so on integration we will get, now integration of this term will be your c square z square plus 1 power 3 by 2 upon 3 by 2 equal to cx plus y plus some another constant of integration, say d. So this is your answer, and we can write it as, this 2 is cancelled. So we will have 1 upon 3c square c square z square plus 1 power 3 by 2 equal to cx plus y plus d. So this is your answer. So we have solved the problem number 3. I think 4th is easy, so I am solving the problem number 5th. So q equal to, let assume f equal to q minus z plus px whole square. Then Charpit's equation is Charpit's auxiliary equation is dx upon fp, and you can see that the differentiation of this term f with respect to p will be 2 times, and the differentiation of p will be your x. So this will be your 2 times x into z plus px, and this is equal to dx upon fp. Let us write formula first. So this is your dx upon fp equal to dy upon fq equal to dz upon PFP plus QFQ equal to minus dx upon and then dp upon fx plus pfz equal to minus dq upon fy plus qfz. So now from here, if we put the value of fp, we will get dx upon fp. Now your fp will be minus 2x z plus px and equal to dy upon fq. Now your fq will be 1 dz upon, there is no need to write this term because we will not get anything from this term, and this is equal to minus dp upon fx. Now your fx will be minus 2 times p z plus px equal to plus p into fz. So this is equal to minus dp upon fx. Your fx means minus 2 times z plus px into p. Then we will have p times fz. Now p times of fz will be, again this will be minus 2 times. Now the difference of this term with respect to z will be 2 times z plus px into p. So we will have minus 2p. And this is equal to, from here we will get minus dq upon fy. Now as fy is 0, so because there is no term of y, so this will be your fy is 0 plus q times fz. Now fz is, again your fz will be minus 2 z plus px. Okay, this is your Charpit's auxiliary equation. Now here you can see that this is your minus 2q z plus px and this is your minus 4p z plus px. So we have a choice to take either dp or dq, or we can also take dx and dq. In case of dx and dq, you can see that minus 2 times z plus px will be cancelled and we will have dx upon x equal to this minus minus plus dq upon q. So it is easy to take dx upon this term and dq upon this term. And in case, I think if we take these two terms, then we will have some calculation problem. So I am not writing these two terms here. I am taking the first term and the last term. So on taking the first and last term, taking first, say this is your first, second, third, fourth and fifth. And fifth term, we get, now this will be your dx upon minus 2x z plus px is equal to, from here we will get this minus minus plus dq upon 2 times q z plus px. So, or you can say that dx upon minus 2 minus x equal to dq upon q. So on integration, we will get log x. So this minus sign is here, equal to minus log q, or you can write it as here. So this will be minus log x equal to log q plus some constant of integration log c. So from here we will get log x power minus 1 equal to log cq. We know that log m power n is n log m. So x power minus 1 equal to cq. So your x will be, your q will be 1 upon c into x. 1 upon c can be written as 1 upon c can be written as some constant a. So therefore your q equal to a upon x, where my constant is 1 upon c. We can take any constant, so there is no problem on taking constant as a. So this is your q. Now with the help of this q, we will evaluate our p. Now using, because q equal to z plus px whole square, so as our q is a upon x, so from here a upon x equal to z plus bx whole square. So on taking square root, we will get square root a upon square root x equal to z plus bx. So our p will be root a upon root x minus z divided by this x. So this will be this one. So now we have the value of p and q. Now let us use the formula of dz. Now dz equal to p dx plus q dy implies now your p is on root a upon x root x into dx, and again we have z upon x, so into dx plus q is a upon x. So this is your dz. Now let us integrate this term. As you can see that here our x is common. Now we can also write this term as dz equal to root a upon x power 3 by 2 into dx. Then here we will have minus z upon x dx. Then the last term is a upon x dy, or write it as x root x. Now take the LCM. Now take this x common. If you take this x common, then in the left hand side we will have x dz, and take this minus z dz on the left hand side, minus z dx on the left hand side. So we will get z dx equal to root a upon root x dx. Then we will have a into dy. Now this left hand side can be written as d times xz. If we write x, then the differentiation of z will be dz. Then on taking z as a fixed quantity, differentiation of x will be dx. So we can write it as dxz equal to root a into x power minus half dx plus a dy. So on integration, we get xz equal to root a. Now the integration of x power minus half will be root x. Now the integration of x power n is x power n plus 1 upon n plus 1. So we will get root x divided by 1 by 2 plus a y plus some constant, say b. So this is your answer. Xz equal to 2 times root a into x plus ay plus b. So this is your solution. Now let us solve. I think my problem 6 and 7 are easy, so you can solve them. I am solving the problem number 8. So solution of the 8th problem. I think this has some calculation problem. So let f equal to p square q plus q square y minus z equal to 0. So Charpit's auxiliary equation is dx upon fp equal to dy upon fq equal to dz upon p fp plus qfq equal to minus dp upon fx plus pfz equal to minus dq upon fy plus qfz. So this is your Charpit's auxiliary equation. Now let us put the values of various partial derivatives. Now fp, the partial differentiation of this term with respect to p will be your 2px, and this is equal to dy upon, again this will be your 2qy, and I think there is no need of this term because it do not give any calculation. So I am writing it as pfp plus qfq, and this is equal to minus dp upon fx. Now the partial differentiation with respect to x will be p square, then p into fz. Then again this will be your minus p. The partial differentiation with respect to x will be p square, then we will have p, and the partial differentiation with respect to z will be minus p. And this is equal to dq upon fy. Now again fy is q square plus qfz. Now this is your minus q. Now we have some calculation problem, because now it is not easy to solve this dp upon this term and equal to this dq upon q. So let us take some other multiplier. So now this is equal to, let us write this term as p square dx, 2p dx plus p square we can write it as 2p dp plus p square dx. Let us take these two terms and let us see whether it works or not. Now if you take this term, then you can see that means I am writing this numerator, I am multiplying this numerator by 2px, and let us take this minus sign in the denominator and here the minus sign in the denominator. So if you multiply this numerator by 2px and now multiplying this denominator by 2px, let us take this minus sign here, then we will have p square minus p, then p square into dx. Now dx is this 2px. And let us take one more similar term, which is your 2qy dq plus q square dy. And let us see what do we get. So here we will have 2qy dq. So from here we will have minus 2qy, then q square minus q, then plus q square into dy. Now the term, here we have to multiply this term by 2qy. Okay, now as we know that all these ratios are equal to each other, so let us take these two ratios. So from here, now you can see that the numerator is your d of p square x, and I have written it in such a way that so that we can combine these two terms. Now on combining these two terms, we will get d of p square x, because the differentiation of p square will be 2p and then the differentiation of p will be dp. Similarly, then if you take p square as a constant, then the differentiation of x will be dx. And let us see this denominator. Now you can see that this minus 2p qx and this plus 2p qx will be cancelled. So we will have minus minus plus 2p square x. So if we take p square x t, then this will be your dt upon 2t. So thus we have some easy calculation. So this is equal to, here we will get d of q square y, and similarly now you can see that this term and this term is cancelled. So in the denominator we will have 2q square y. So this is equal to, now integrating this term, now if you take p square x as t, so this will be your d of p square x upon p square x, and in the right hand side we have d of q square y upon q square y. So if you take this term as t, then this will be your dt upon t, and here we have dt upon t. So on integration we get log p square x equal to log q square y plus some constant of integration c. So from here we have p square x equal to c times q square y. So now you can find any value, either you can find the value of p square or q square. So let us find out the value of p square. So it is equal to cq square y upon x. So from here, because p square x plus q square y equal to z, so put the value of p square here. So this will be your cq square y plus q square y equal to z. So from here, q square y is common, so in the bracket we will have c plus 1 equal to z. As you can see that c plus 1 is constant, so if you want to write it as, you can write, but we can also take it as some another constant. Under root c plus 1 is constant, so write it as some another constant. So now, and if this is your q, so hence our P will be, hence our P equal to, now this P will be Q times under root C y upon under root X, and this is equal to root Z upon root Y into root C plus 1. This was the value of Q, and into root C into root Y upon root X. So you consider your root Y is cancelled. So this is equal to root C upon root C plus 1 into root Z upon root X. So we have these 4 terms, and this root Y is cancelled. So therefore, now dz equal to p dx plus q dy implies dz equal to p, and your p is this term root c upon root c plus 1 into root z upon root dx into dx, and your q was root z upon root y into root c plus 1 into dy. So here you consider your root c plus 1 is constant, so we can take it on the left hand side, and the right hand side we have root c into root z upon root x dx plus root z root y dy. We can also divide this equation by root z. So if we divide this equation by root z, we will get this term. So on integration, you know that integration of z to the power minus half will be z to the power half upon half. So here the integration of the first term, you can take this root z in the numerator, then this will be your z to the power minus half, and its integration will be root z upon half. And on the right hand side, again we will have a root c into root x upon half. Then here we will have root y plus some constant integration of b divided by again half. And let us divide the whole equation by, or you can say multiply the whole equation by 2. If we divide the whole equation by 2, our answer is root c plus 1 into root z equal to root cx plus root y plus d. So this is your answer. So this is our answer.